السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, today we will continue talking about or finishing up the k-means clustering algorithm and some issues about it. And then, if we have time, we will start a new session. Do you have any questions from last time? What did we cover last time? Clustering. Okay, what is the main concept of k-means? What's the idea, main idea? Yes.
Making clusters, grouping server data in groups.
Similar points will be in clusters or groups. Yes, based on what? How can we measure similarity?
Distance.
By distance. Okay, by distance. Okay, so distance in, of course, the feature space. Okay. And we went through the algorithm and even we saw some visualization. Did you try to play with this tool? Okay, with different distribution of the points. Okay, good. So today, inshallah, we'll, as I said, we have a couple of issues with k-means that we will discuss first. The first one is whether the choice of the initial centers will affect the clusters that we will get eventually or not, and how severe is that. And the other issue is how to choose k, because k can be considered as a hyperparameter. So how many clusters we should get? So these are the two issues that we will start with, inshallah. The first one is the impact of initialization. So first, do you have an idea whether this will really have an impact? Yani if we choose the initial centers, okay? Of course, as we discussed last time, in the vanilla standard algorithm of k-means, the initial centroids are randomly chosen. Will that affect the final clusters? Yes, and here is an example. Let's say that we have this data. Of course, ideally, how many clusters we should have here? 3, right? With this data, it seems like we have 3 clusters. Type. If I have chosen the centers, the initial centroids, to be one in each group, so one here, one there, and one there, we would get the 3 clusters easily, right? Maybe in 1 or 2 iterations we will be done. But here, because the centroids are selected randomly in the beginning, it happened that we have these centroids. We have the green one, we have the black one, and we have the red one. So what you would expect here? Where are the clusters will be? So how many clusters we will get eventually with this? 2 or 3? 3. Anyway, it will be 3 because we have 3 centroids, right? So we will get eventually 3. Okay. By the way, it can happen that one of the clusters to be completely empty in general, but still we will get 3 clusters. Whatever the k is, we will get from the k-means algorithm, we will get the k clusters. Okay, as long as we have at least k points, of course. Or even I think even if we don't have k points, but that's of course you should not expect number of clusters to be more than number of points, of course. Type. Now, where will be the clusters in this case? What do you expect? 2 here? Here. We will have 2 here because we have 2 centroids here. So what will happen is that these points will be distributed over the 2 centroids. Okay, so half of them, probably the lower half will be a cluster and the upper half will be another cluster. And how about these? Will be probably one cluster, right? Because these points are closer to the red centroid than the other ones, or closer to this one than the 2 other centroids. Okay, and this is exactly what will happen. So we'll have one big cluster here and 2 small clusters here. And that's, of course, not ideal, right? Of course, it is very clear in this example, this easy example, but that indicates that the choice of the centroids will severely sometimes affect the final clusters. Type. How can we solve this problem? There are many solutions, by the way. I mean, this is the standard or vanilla k-means clustering. There are many variants of k-means on how to choose the initial centroids. but we'll not cover them in the course. You are, of course, welcome to explore them. But at least this indicates that if we will use the standard k-means clustering, then probably it is worth repeating the clustering multiple times and looking at the clusters that you got. Okay, because it might happen in one case that the centroids, the initial centroids were really bad or badly distributed, so the final clusters will be affected. Okay, so this is something to keep in mind. So the initial values of the centroids will affect the final clusters. Right. The other point that we want to discuss is how to choose K. Yes, question?
Do we consider this as inductive bias?
How is that? Inductive bias means an assumption, right?
Yeah.
What is the assumption here?
Assigning bias into different versions.
That's how the algorithm works, right? But that's not an assumption. Okay, it's a consequence of choosing of having random initial centers. Okay, but I don't see it actually an assumption, because sometimes it will work. And if I have chosen the centroids here, in one here and one there and one there, it will be perfect, right? Okay. Type. The second point is how to choose K. What is K? K is the number of clusters, right? So we can think of it as a hyperparameter, but we will not be able to tune it the way that we discussed before. Okay, the way we discussed before was for classification. We have training and div and test. We can use the div set to tune the hyperparameter. We don't have in clustering. We don't have training, div and test. Okay, it's not a classification problem. So we are clustering the whole data. So we'll have to find a way to pick the right K. So here's one way. Here's one way. What is the intuition behind this method? First, to choose K, we need somehow to measure the quality of the clusters, right? One way of thinking about it is that each cluster should be tight enough, should be homogeneous. The points in the cluster should be close to each other and to the centroid as much as we can. Okay? So if the final clusters, each cluster, the nodes or the points or the examples in that cluster are tight, are close to each other, then that indicates that these clusters are good, right? So we can measure if we go back to this example and forget about the centroids for now. If we look at this, if we consider this is a cluster, okay, and we compute the distance between each point here and the centroid. Imagine that the centroid should be somewhere in the middle of these points, right? If we compute now the distance between every point and the centroid, and we sum all of these distances, the summation at the end will be very small, right? Because these points are close to each other. If they are far, then this number will be higher, right? So if we keep doing that for every cluster, we measure somehow how the points are far from the centroid. And we do that for every cluster. If we sum over all the values for all clusters, then if we get a small number, that means that all the clusters are tight, are homogeneous. The points in each cluster are really close to the centroid. Right? And that would be good or bad? Good. Will be good clustering, right? Because we want, that's the goal of clustering, is to put together the points or the examples or the items or the products that are close to each other in one cluster. Okay? So this measure that we discussed, or at least motivate, is called within sum of squares. But we don't only compute the distance, we square it. If we look at the summation here, forget about the first one. The second one here, the inner one, is going through all the points in one cluster. Okay? And the centroid of the cluster is Ci. The cluster is number I. Ci is the centroid of the cluster. So we compute the distance between every point in the cluster and the centroid. And square it. so that we can punish more the points that are very far, because the points that have longer distance, when it's squared, it will be even larger. Okay, so we sum over all of these squares of distances. That would be for one cluster, and we repeat that for every cluster. That's the outer summation. Okay, this is called within sum of squares or within cluster sum of squares. Okay, type. That will give us a measure about the quality of the clusters. Okay, type. What can we do with this measure? We will plot for every number of possible clusters that we think about. We plot the cluster versus this measure. So we will get something like that. We'll start with one cluster. Okay, when we have one cluster, of course we would expect that number to be really big, right? Because the points are scattered all over the feature space, right? So if we compute the distance between every point and the centroid, it will be very far, right? So we expect that number to be very high in the beginning, and then it will decrease with increasing the number of clusters. Now let's think about the extreme. What if we have, for example, 100 points and k is 100? Okay, k is 100. So we want to get 100 clusters out of 100 points. So overall, okay, approximately we will get one cluster per point. So every point actually will be one cluster. Type. If that's the case, what will be the number here? What will be the measure? 0. Why is that? Who said 0? You. Why is that? Because the distance between the point and itself, which is the centroid of itself, will be 0. So over all clusters will be 0, right? So as we increase k, of course that number will decrease. Right? Right? So it's not intuitive to minimize that number. Otherwise we will get k to be the number of points. Right? Right? So there must be another way. So the heuristic that we use here is called the elbow heuristic. What does that mean? We will look at the curve. The curve initially, you will see that there will be a steep slope in the beginning, a fast decrease. And then the decrease will be smaller with increasing k. As you see here, the decrease was very fast between 1, 2, and 3. Then slower a bit, okay? Then even slower. We will look at where the point after which the curve will be almost linear. Which, if you look at this, you will see that after 5, the curve will almost be linear. Okay? That point is called the elbow. That point is called the elbow, where after which the curve will start to be almost linear. And this will be the value of k that we should consider. This is just a heuristic. Of course, it doesn't guarantee that we will get the best number of clusters, but that's one way that is used in the field. Okay, did you understand that? So you understand how we can plot this curve? Number of clusters on the x-axis and the within sum squares on the y-axis. There is one value, of course, per value of per k, the value of the number of clusters, and then we will observe the curve. Whenever the curve starts to be linear, then the point before it, okay, which it's like separating between the steep slope and the very slow slope, very small slope. Yes.
دكتور بس احنا مشكلتنا في الانيشال فاليو تبعت الكي مش في عدد الكي صح؟
الاثنين both.
بس ده بيحل مشكلة عدد الكي صح؟
Yes.
طب
Yes.
والانيشال فاليو
Initial values you have to, with the vanilla k-means, you have to repeat. Okay? You have to repeat. You can, by the way, combine both. You can repeat and then compute the within sum squares to see if it's now improved or not. Okay, with the same k. Here you can actually minimize. You can get the initial centroids that will give you the best value of the within sum squares, which is the smallest, but within the same k. Okay? Because naturally when you increase k, this value will decrease with most of the cases. To the extreme that we mentioned that it will be 0 when k is the maximum. Okay, so this curve will touch the x-axis at the end. Okay, anyway, so we are not looking for the minimum value, we are looking for the elbow here. Okay, the intuition here is that the clusters, the homogeneity of the clusters is almost started to be stable at that point. Okay, so we don't want to increase the clusters to the maximum, but we want a value where the homogeneity is stable. Okay, that's, I think, the intuition. Any questions about that? Okay, here is an example of clustering in general. So here is an image where we want to cluster the points based on the color, not based on the position, based on the color. Okay, so in this case, what will be the features that we consider? X and Y? X and Y are the coordinates, right, are the position. But we are not interested in the position, we're interested in the color. So what should be the features in this case? RGB, if we use the RGB color space here. Okay, so 3 values, red, green, blue, the values of each point. Okay, and based on that, we cluster. Okay, so when we use 3 colors, here is what we will get. Sorry, not 3 colors, 3 clusters. Okay, 3 clusters. When we cluster the points using their color into 3 clusters, we get something like that. So we get that the color of these points are similar or close to the color of these and close to the color of these. Originally, that was red, and green and yellow, right? Yeah. And that's the blue one, and the others are almost black. Okay, so these are the 3 clusters that we get. Do you see the clusters here? Okay. Here is what we get when we have 6 clusters. Okay, so we start to see points more detailed, right? The colors here are more fine-grained. So some small changes in the color will assign different clusters to pixels of different colors here, even if they are close. So you can see that this here we had this and that in one cluster. Here you see that they started to be 2 clusters actually. We got even a cluster that is different than the black one. Okay, so you start to see more details. When you increase the number of clusters, you start to see more details or distinguish more details in the image. Okay, this is just an example. Any questions? Any questions about clustering? So what remains is just to quickly discuss use cases. Here we have like 3 or 4 use cases. One of them is clustering patients based on their medical measurements. So here there are measurements that will help cluster the patients based on their risk of having heart diseases. So clustering is used here to cluster the patients into different clusters based on their measurements. Another use case is to recognize objects in images or videos. We started to see that in the previous slide, right? So clustering can actually, if you have objects and the objects, for simplicity, objects are having different colors, then you can actually recognize different objects this way. If you started to cluster the points. Of course, you don't have to only limit yourself to colors. Maybe you can also add the position and see when you add features about the coordinates plus the color, you might get something that's more interesting. Okay, so clustering is an exploratory tool, which means that you have to explore with different values of clusters, with different features, maybe with different even distance measures. You can use different distance measures based on your problem.
دكتور
Yes.
الكلاستر ما بينطبقش عليه المبدأ تبع الأوفر فيتنج والأندر فيتنج صح؟
Good question. No, usually we use overfitting, or we use the concept of overfitting and underfitting more for classification. Okay, but you can think of it also here, but it's not usually discussed this way. But if you increase the number of clusters, this is similar to what? Overfitting, because you are looking at very small number of examples in each cluster. Okay, but we actually don't usually discuss overfitting in clustering. Okay. Any more questions? Okay, طيب. Now we'll switch inshallah to a new session. I think we have a few minutes just to give an introduction. What are the sessions that we covered so far? We started with introduction, right, and in which we studied the first learning algorithm, which was what? Decision trees. And then we studied the second session about limits of learning, where we started to see why machine learning can fail, what are the sources of errors, why we need to split the data into training, div, and test, right? All of these concepts, which is a very important concept. And the third one was about nearest neighbors, and we saw two applications of nearest neighbors, which is KNN classification and k-means clustering. And you see that they are really related, right? They are both based on computing distances between points in the feature space. The fourth session is a bit different. We will, as usual in the course, we will always study a new model every session. So the model that we will study, inshallah, in this session is called perceptron, which is very important for a very valid reason, because it is a good introduction and the basis for what we call neural networks, which is the basis for what is called deep learning, which is the state of the art now in machine learning. So this is very important for that reason. Inshallah, we will touch, I think neural networks, we will have like three weeks for it. And at the end, we will start to talk about deep learning, but this is the basis for it. Okay. What we will cover, as I said, we will cover a new model or algorithm called perceptron. We'll talk about also variants of it. And also, while we are doing that, as usual, we will also discuss some concepts, okay, some general concepts. In this session, we will talk about online versus batch learning. We'll talk about error-driven learning. And we will also talk about linearly separable data sets. Why we need that model? If you recall, in decision trees, with maximum depth, we limit our attention to few features, right? Even if we have 100 or thousands or million features, if we have a maximum depth of like 5, for example, then we will look only at 5 features, right? At least in each path. So we will focus with decision trees on few number of features, usually. In KNN, it's the opposite direction. We actually treat or use all the features, right? There's no way in KNN to say I will only focus on these features, or these features are more important than the others. There must be some way in between, where we can say we want to use many features, but some more than the others. What does that mean? We want a mechanism that will give priority or weight or importance to features, so that one feature will be very important, so it will be getting more attention in the prediction, and others might have lower priority or lower importance. Okay, so the idea here is that we will really give a weight for each feature. If the weight is high, that means that this feature is very important in prediction. If the weight is low to 0, that means that it doesn't have any importance or doesn't have any impact on the prediction. Okay, So that's the main idea. The perceptron algorithm will help us learning weights for features. We didn't have that. We have some of that indirectly in decision trees. Okay, but it was like binary. It's either in the tree or not, right? So it is like giving weights, 0 or 1 weights for the features. In KNN, all of them have the same weight, have the same importance. With perceptron, we will be able to learn a weight for each feature. So some weights will have very high, some features will have very high weights, so they will be important in predictions, and some will be very low. And let me give you an example to give you an idea about these weights. If we are designing an application for sentiment analysis, what do we mean by sentiment analysis? Knowing whether a review for a specific product, like a book or movie, positive or negative, okay, from the text itself, automatically, of course. Okay, so if we consider the features to be the words in the review, then a word like great should have a high weight, right? Because it will indicate that this is a positive example. On the other side, a word like terrible should have high weight, but in the negative direction. Should have a higher negative weight because it indicates negative class or negative review, right? Both are important, but one is positive and one is negative. On the other hand, a word like movie will be useless, right? In knowing whether this is a positive or negative review, right? So the weight ideally for the word movie in this case will be 0. Okay, so that's the ideal weight. That's the meaning of the weights here. If a feature has a large absolute value of the weight, like large positive or large negative, then it has an importance or it has a priority in taking the prediction decisions. Okay, if we have the ability to do that, then that might give us better predictions. Type. I don't think we will have time to go through this today, but this is what we will start with, inshallah, next time. We will we'll talk about neurons, which are the units in the main units in our brain mechanism. Okay, so we'll talk about neurons, and we'll then talk about how we can represent them and how we can use just one neuron as a classifier. And then after we do that, I think 2 or 3 more weeks, we'll talk about how we can connect many of these to have a network of neurons, which is called neural network. Okay? So inshallah, we'll see you on Thursday. Assalamu alaikum.